So status update, the components for the new user port interface, including the Commodore 64 edge connector, which I've just tested and it seems to fit well, and also the ribbon cable, which will take me from the user port breakout board, which is over here, into the user port interface. So everything has arrived today, which is very nice. And also the sprite boards, which were in the same box, have also arrived, but I haven't ordered the components for the sprite boards yet, because I want to get this one built first. And then when this one's working, then I can order the components for this one and get this one working too. But yeah, I'm going to have a nice evening soldering up this one and then seeing if it will actually work properly. So with the user port interface, the breakout board comes in here, into the bottom here, and then it will output extended memory bus and the 34-way memory bus interface plus the data here. Plus, it will also be emitting, or rather the interface, the user port interface board will be taking the signal line for the VBlank and actually outputting it to here too. So this is input, output, and these are output to the memory bus, and then this one is going to be input for the VBlank interrupt, which I've been testing already with the simple 4-bit user port memory interface, which is on the prototype board, but this one has auto incrementing address, which is going to be a lot quicker because I can just do a store, an absolute store actually, which is only a few cycles, straight to the user port, and then it will auto increment the memory address in the 16 bits bus here, 16-bit memory address on the memory address bus here. So it will actually allow the Commodore 64 to update a lot more information rather than shifting around bits, 4-bit values into different registers and latching them and all sorts of stuff like that. So this board here is going to be relatively simple. There's only three components. There's the edge connector, then there's the IDC connector, and then of course there's going to be a little switch or jumper here. I'm going to put a simple little switch here. I've got a small switch for the reset here, so I'm actually adding a little reset button to my Commodore 64 as well, just because it would be, it seems a shame not to when you're putting a user port interface breakout board to put a reset button. So yeah, great. I'm going to look forward to that this evening, and hopefully it won't take too long to. I've got all the sockets and everything, so this is all one order. All of this goes in here and here. Such a big box for such a small bunch of boards, but you can see how large the sprite board is. The sprite board is going to be a huge task to solder up, but an enjoyable one nonetheless. So, short update. I've finished the soldering on the user port interface board, and I've also finished the soldering on the user port breakout board, which is this lovely one here. So when this gets plugged into the Commodore 64 like this in the back, then the cable here can loop out and come into here, which is much more sensible than previous arrangement where it was going around the different prototype boards. I have not populated the ICs on this yet. It's getting quite late, so I'm going to do that tomorrow evening. But what I've done quickly is that I'm checking to make sure that the regulated 5-volt supply is able to connect through the socket here, which it does, and then supplies power to here, and then obviously I've kind of connected up the intended memory bus and the interrupt line and everything else on this side, so we can start seeing how it stacks up. And yep, the clock crystal. Clock is not really a crystal. The CAN oscillator is seated as well, so I don't forget which way round it's meant to go. And just to make sure we have a good steady picture here, and actually the picture is looking pretty darn good. The box here is showing quite correctly that it's still seeing an RGB H and V signal with 264 and the correct timings and everything on AV3. So that gives me the confidence now that I can go ahead and populate this board, which I will do tomorrow. So good. I'm glad that it seems to be mostly working so far. So progress with the build this evening. I've populated the auto-incrementing 24-bit address bus user port interface here. I've connected it to the Commodore 64 because the Commodore 64 is really meant to drive this. I've also connected up the address and the data bus to the logic analyzer so that I can debug the board as it's connected to the video generation board and the character layer underneath. So now I've been updating the code. Well, okay, so this is the test case, which initializes, oops, hold on a second, there we go. This is the test case which initializes a new video display, but this time the test case differs because it uses the user port to 24-bit bus interface rather than the simple one. This is the one with the auto-incrementing 16-bit address. In theory, it's a lot quicker than the other one because there's none of this 4-bit flip-flopping around to program all the latches each time. What it does is that it uses the underscore PC signal on the user port, which after the 8 bits of data are output to the user port, this goes low and then high to indicate that there's a new byte of data, and it does that with 1 megahertz clock, I think it was. So this board then traps the low to high transition, the positive edge of the underscore PC, and it uses that to first of all trap or latch the extended memory bus byte, then the low and high memory address, and then every single byte after that, unless PA2 is asserted low and then high, which resets the whole latch process. Every byte after that, which can be stored at up to 1 megahertz speed, but store accumulator or X or Y absolute to the user port does not take 1 clock cycle. So it's not going to be 1 megahertz, but by the by, the board will trap each byte written and then output it for a small amount of time, because what it does is that it uses this clock here, this one, which is currently running at something higher than 1 megahertz, because it doesn't matter. What it does is that it traps each byte thereafter coming from the Commodore 64 user port, and it outputs it, and then it increments the address bus. But what it also does is that it returns the address bus, including the extended memory bus byte, to 0, so it's not asserting any extended memory bus architecture on the video hardware, which means that there's no contention. So it does that with a minimal write pulse, which is very important because this is a big improvement especially with the 16-bit auto-incrementing memory address. It means that the Commodore 64 can just do continuous if it wants to clear the whole of memory or copy large chunks of memory. It just does continuous store accumulator or X or Y absolute to the user port data bits output, and then it can do that as 1 byte as a chunk. So every byte is auto-incremented and auto-written to an auto-incrementing address in the video hardware, which is actually a lot quicker. So this test case was updated to use this user port memory interface. I've updated the code to add on all of the functionality for doing a vsync or safe write in the vblank. I've speculatively changed this to 50 based on the test case. So if I execute the test case with, say, 64, the simulation should show, here you go. So if I press Control now, we'll see up in the top a little bit of contention in the simulation, or emulation rather. Just a little bit. You can see that whenever I press Control, you can see the little contention bytes coming. So what I did was that I reduced it to about 50. Now the emulation is not clock cycle accurate to the Commodore 64, but it has a fairly good approximation. So I've reduced this to 50 in anticipation of needing that value on the real hardware. So what this means is that, so the previous code was only able, with the 4-bit alternating latch model, the slow user port interface, was only able to copy 8 bytes per vblank because the Commodore 64 was doing an awful lot more work. This indicates under emulation that if I press Control now, you don't see any contention information up at the top of the few raster bars here. So this indicates that the faster user port interface with the auto-incrementing address is many times faster because it can transfer 50 bytes per vblank instead of just 8 bytes per vblank. That's the theory. So what I've been doing is that I've been using my logic analyzer to test all of this. So what I can do now is that because I've used the test case to run this code once it's built it, so what I can do now is that I can set up the logic analyzer to trigger here on the memory write flag on a low transition. This is the memory write flag going to the video hardware. Up here, I've set up this bottom 16 bits signals to be the address, and then the next 8 bits is the data which is going to the video hardware. So if I set this executing, okay, and then so it's waiting on a trigger on the high to low transition, the negative edge of the memory write signal. So then I send this over to the Commodore 64. Where is my easy transfer? There's my easy transfer. So I set this to the Commodore 64, or send it to the Commodore 64 rather. There we go. Commodore 64 is doing stuff, and there we go. Almost immediately we get some indication of data. Now the bus reset basically does a memory address bus write with all zeros, so that's fine, that's no problem. And then I see that there's some kind of address being asserted here. So let's scroll over to here, and then let's zoom in. Let's scroll to the next transition. So we can see here that there's a little low memory write pulse, so we'll keep on zooming in. And this is looking fantastic already. So I don't know if you can see that. I'm going to try and zoom in a little bit so you can see. So the address bytes are 9C00, which is correct because the first address that I start writing is actually the palette. And there's a little memory low write pulse here, and that occurs just after halfway of asserting the address bus and asserting the data that I want to send, and the data in this case is 0. If I then go to the next transition, pressing N on here, go over a little bit more, we can see when the memory write line goes high, of course, we can see over here that the address bus is 0, the extended memory address bus is 0 as well, but I haven't connected that up in terms of signals. I'm kind of assuming that it's correct because the address is correct at this stage. And then the next address is 9C01. The memory write pulse goes low here, again, just after halfway. And then the next transition should show memory address 9C02, excellent, 9C03. So following on from a successful test with the logic analyzer, I decided to reorganize my desk space. So the Commodore 64 actually doesn't have a normal TV display. Now I've decided to get rid of the other monitor because it was cramping my desk a little bit. I've removed the logic analyzer from the 3-board setup here, and I'm just going to try now with the Commodore 64 driving pretty much the same code. I did do some tweaks to this just with the scrolling and some of the data transfer. So this is what we should see. This is the emulation. And then if I press Control, which is space on the Commodore 64, then it refreshes the screen once, press Control again, and then we should start seeing the background kind of like scrolling to the left, a character at a time. So where is my easy transfer? There's my easy transfer window. I'm just going to browse for the prog file here. There we go, the compressed one, which is about 17 kilobytes. Hit go, Commodore 64 is on, it's up there, and there we go. So the corrupted screen or partially corrupted screen is normal. We expect to see this because we're uploading information during the VBlank. So now when I press space, it uses the VBlank synchronization copying routine. And there we go. We have a lovely, perfect display. It actually looks really good. I'm really pleased with the color quality of this. The color quality is actually pretty good compared to the emulation as well. And the colors maybe look a little bit washed out, but that's okay. So if you remember the video generation board, I actually had the option of having pots on the RGB component. So if this color saturation is a little bit of an issue, then I can put some pots in and then I can tweak those values around until I get something which I'm happy with. But generally speaking, I'm happy with this color balance. So I've pressed space and it's scrolled one character to the left. Keep on pressing space and we see that we could get some character scrolling to the left. Now this is the character screen. It has 1024 characters. It's not really character definitions. It's not really designed for scrolling. Actually, it's designed for more kind of like static score or partially static score displays and player lives and stuff like that over the top of everything else, or underneath, or wherever the playing priority is decided to be configured. But actually the real layer, which deals with a lot of fine pixel level scrolling, is the tiles, 16 by 16 tiles layer, plus the Mode 7 layer, of course, but the 16 by 16 tiles layer is going to be the next one that I build after the sprite layer. And that one has the ability for split screen scrolling horizontally and vertically as well, depending on how it's configured. And it has quite a large, virtual display field which can be scrolled around as well. But generally speaking, I'm really happy with the way that this character layer has come out. The new user port board is a lot faster than the 4-bit alternating, memory copying board which was on the prototype board. So yeah, it's a really good proof of concept. And actually, the copy loop that I'm using in the code is actually not that optimal. Still, it's still quite general purpose, even though it's doing counts of the number of bytes that it's output before doing a sync for the VBlank and stuff like that. This is not really needed. What's really needed is to unroll this tiny little piece here to speed code and actually have an optimized routine which does byte copy, byte copy, byte copy, byte copy, byte copy, and maybe up to 64 byte copies or maybe even more, and then do just a wait for VBlank and then do another unrolled loop and so on and so forth. Copying the whole screen that way would be over 12 kilobytes worth of code. But the thing is that we've got the cartridge port free on the Commodore 64, so we can use a couple of cartridge banks, no problem, for any kind of optimized screen copy or copy into the sprite registers from the C64's RAM to the video hardware RAM over the user port bus. So I'm not too worried, to be honest, about the speed of that. And because the cartridge port is actually free still, we could use extended features like DMA transfer for cartridges that support this. So reading bytes from the Commodore 64's memory and then storing that byte to the RS-232 register, for example. And that would be feasible, I think, with a lot of DMA transfer modes for lots of different types of cartridges that support DMA from the Commodore 64's memory. So we could try that kind of thing too. That would be interesting. It's kind of like similar to how you might stream bytes from the Commodore 64's memory to a static memory address for the SID chip volume register to play samples. On a timed basis. It's a very similar concept, except that you're streaming bytes from Commodore 64's memory to the user port. That's all it is. So yeah, really good test, really pleased with this. There were a few tweaks, of course, to the user port board, hence the usage of the prototype board, but that's okay. These things are expected with prototype boards, and I'm going to be ordering a replacement for this user port board, and you pulling out the ICs here and just transplanting them into the new board, getting that working is going to be something that I can do quite cheaply and quickly, because the Chinese company that fabricates these PCBs is really reliable. I'm very happy with them, and they quote really good prices, so I'll continue to use them. Right. Anyway, very, very happy with this. Well, I might try some different pictures with this. I might do a slideshow. I could use a cartridge with my trusty Easy Flash 3, and basically, every few seconds upload a new image from the cartridge memory. via the Commodore 64's RAM, so I could compress them and then send it to the video card. You know, a slideshow would look really nice. I might do that. There are other options too. So after I build the sprite board, which I've already got the PCBs for, I just need to order the parts for. I could do all sorts of different static screen arcade games just with the character layer alone and the sprites layer. Arkanoid, for example, springs to mind as a really good example of a game that doesn't really need scrolling. It needs sprites and a nice colourful character screen. So there are various different options there. So yeah, really pleased with this progress. Onwards and upwards.